Welcome back, everybody. We're going to try to treat the likelihood principle, and we're going to treat it pretty gently today. So there's a lot of statements in the book concerning the likelihood principle, and all I need you to know is this statement right here. The likelihood principle basically says this. If two likelihoods are proportional to each other, and theta has the same meaning, so I'm trying to estimate some parameter theta. If I were thinking about maybe this example right here, the parameter of interest might be P, the probability of a coin landing on heads or tails. So if two likelihoods are proportional to each other, inference is based off of X or Y should be the same. So two likelihood functions are the same, i.e. they're the same wiggly curves, then the information about theta, what it's saying about theta should be the same. And I think that makes some sense. I've been saying that basically since we've been touching the sufficiency principle. So I've at least convinced Josiah that, yeah, that makes sense. So, and moving on. So I think it does make sense that it might if you subscribe to likelihood functions in the first place. I don't think likelihoods are nearly as controversial as they were when Birnbaum presented this theorem. Now, the book says, if you read through the proof on the likelihood principle, it says that this is an immediate consequence of the sufficiency principle and the conditionality principle. And I would say it's certainly a implementation of both of those things. So we're conditioning on the data, so our inferences are conditional. They're not this thing where I'm going to average across more extreme data, where I'm going to think about things as n goes off to infinity. I'm actually just conditioning on the data set that we see. And we're conditioning on the whole data set, whatever that is, and so we're abiding by the sufficiency principle. So we're abiding by the conditionality principle, i.e. we're doing a conditional analysis. I haven't formally defined the conditionality principle for you, but basically it means you're conditioning on your data. So, and I think we could just leave it there. So we don't need any mathematical notation. We know what it means to condition on our data. And likelihood functions do that. And they have the sufficient statistics built in. They say that the converse is also true. That if you adhere to the sufficiency principle and the conditionality principle, that means you adhere to the likelihood principle. That, I'm going to say, is false. So there have been a lot of counterproofs to that proof that Birnbaum has come up with. It's gone back and forth over and over and over again. There's a flaw in your proof, no, there's a flaw in your proof, and the debate continues. So I don't think that this is the only way you can adhere to the conditionality principle and the sufficiency principle, but it does make sense. What other function would I use? They talk about another function in the book called the evidence function. And so it's unclear exactly what you do with the evidence in the evidence function, so I don't even want to talk about it, other than just tell you that the book says something about it. So for example, if you're going to do inference on mu in a normal distribution, they say the evidence is x bar, and if you knew what sigma squared was, you would use sigma squared to calibrate the uncertainty about x bar. So the evidence function is x bar and sigma squared divided by n. What do you do with it? So that's the evidence, I agree, that is the data. The data itself is the evidence. But it's unclear what you do with that and how you build probabilities out of that. So it's kind of an incomplete thought process, I think. So for me, I think the evidence is the data itself, and that's all there is to it, and you want to condition on it. There's the formal likelihood principle versus the likelihood principle. You don't need to read through all of that stuff. There's also another principle called the equivariance principle that chapter 6 covers. We're not going to touch that here. So we're just going to skip ahead to chapter 7 after we run through this example. If you're one of those people that likes to debate things, the likelihood principle, maybe you do want to study this more, but we're not going to turn this into a full-blown philosophy class. So we do have a department on campus that does exactly that, and they love to argue about the likelihood. So we'll let them do that. I do like the likelihood functions. They tell me something. I just want to point out with real data, they don't come with likelihoods in hand. You end up building them anyway. And so it's not like we know for sure what the sampling function is, i.e. we can build a likelihood function out of that. We usually do modeling. So there's an interesting statement in the book that says there's all kinds of things statisticians do that violate the likelihood principle. So most statisticians don't adhere to it. And then they make comments that Bayesians do or fiducialists do. You don't need to worry about that whole fiducial thing. It means that they're treating a likelihood as a probability distribution. So they're basically using a likelihood like it's a posterior distribution. So i.e. the prior is flat or multiplied by 1. People don't think that that's correct anymore. Just do the Bayesian thing. The correct fiducial argument is to do Bayes. I'm going to leave it there. That's my opinion. So nobody touches that fiducial thing anymore. People do Bayes. So there are papers out there that say, like, what is the correct fiducial argument? And here's my paper. It's Bayes' theorem. So done. So, and you could say more about that if you wanted to. Okay, so I think that it kind of makes sense that if these two likelihoods are the same and we're going to follow the same inferential procedures, then we would want our analyses to give us the same information about theta. And so that's what I'm going to say the sufficiency principle, or the likelihood principle is. So let me restate that again. If two likelihoods are proportional to each other, and we all agree to do inference the same way, then our inferences should lead to the same conclusions. So our inferences should be identical. I think that makes sense. So if we all agree to follow the same inferential procedure. So that's that should point right there. So what the likelihood principle does not say is exactly what you should do after you have your likelihood function. Okay. So if you're a Bayesian, it's going to presuppose you're going to use the same prior or something like that for all the same reasons, and I don't think people do that. So anyway, I'll leave it there. Let's consider an example. I think this is probably the more compelling thing is all the examples. We can show what goes wrong if you don't adhere to the likelihood principle. So we don't need a proof, we just need an example to try to understand why Birnbaum was trying to prove this. So let me just say one more time, the likelihood principle is an implementation of the conditionality principle and the sufficiency principle, but I don't think it's necessary that you follow the likelihood principle if you subscribe to that. Saying that, I don't have a better way to implement it. So I'm okay with that. I don't need to say proof. So, willing to entertain all ideas out there. If they work, then they're interesting and let's explore them. Okay, let's consider this example. Let's say I just stumbled across this data set. I'm going to call myself experimenter 1. So we're going to confront two different experimenters again. So experimenter 1, I'm going to pretend to be experimenter 1 for a second. Whoa, here's a data set. That's interesting. I want to do inferences on it. So I'm going to make some modeling assumptions about this data set. I'm going to assume that the probability of H is equal to P, and the probability of a tail is equal to 1 minus P. So the typical Bernoulli setup. So I'm going to imagine that this data was generated in a Bernoulli fashion, i.e. there's just coin flips. IID replicates. So I don't really know if they're IID. If we were going to really do this in practice, we probably need to look at more data on this and see replicates of it and see if it behaves in a independent fashion. So we probably can't tell with this one data set. So if it's IID, let's just presuppose that it is. I'm also, as experimenter 1, going to make another assumption about this. I'm going to assume something about why there's only 10 data points here. So there's 10, you can count them up. I'll also point out there's 5 heads there and there's 5 tails. Okay. So I'm going to make an assumption of why there's only 10 data points. And here's my assumption, that n was fixed in advance of everything. That this sample was generated until there were 10 Bernoulli realizations. So that's an assumption. So another assumption is n is equal to 10, and that was fixed in advance. I don't know if that's true. I just walked up and, whoa, there was a data set sitting here. So I need to assume certain things about it. Let me just ask you a couple questions. Is this a reasonable assumption right here, the first thing? So 1, 2. What do you think? Let me say I am the statistical god today, so I hold the chalk. So I know the answers. It is IID. I'll tell you that much. Everything's IID. So it's exchangeable, maybe I just said. So maybe, maybe not. So I'm going to assume that everything was conditionally generated from this function, and it was done identically every single time. And it has the same modeling parameter. Let's say that's true. So I think this is true. If all that is true, then I think this is reasonable. How about assumption 2? Any gripes? Gotta assume something. So, okay. Now, I'm going to change my hat for a second, and I'm going to pretend to be a different experimenter. So I'm going to call myself experimenter 2. I will point out this example is in your book. They don't have exactly my same numbers. I think their number of heads is 7 minus 5. This is slightly different. Experimenter 2, I walk up, whoa, lo and behold, there is a data set sitting here. I want to do inference on it. I'm going to make an assumption that all of this was generated in an IID fashion, and it comes from a Bernoulli with parameter key. So everything is identically distributed. So 1 probability of H is equal to P, and probability of the tail is equal to 1 minus P. I should probably say that it's probability 0 everywhere else, but we know that these add up to 1 and probabilities can't be negative, so I'm just going to omit that. So experimenter 2 agrees with experimenter 1. So far so good. So possibly we're going to come up with the same inferences. Experimenter 2 is going to think about the stopping rule a little bit differently, and they're going to make a different assumption. So experimenter 1 believes that the 10th trial was fixed. So this is experimenter 1's belief. Experimenter 2 is going to suppose something else. They're going to say, I think that the coin was flipped until the occurrence of the 5th head. So this is the 5th head here. There's 1, 2, 3, 4, 5. So that's the 5th head. And experimenter 2 is going to presuppose that this data set was generated until the 5th head occurred. So what that means is that n was random, or you could think of it as the number of failures is random. So the number of failures plus the number of successes is the number of trials. So you can think about this as failures is random or the number of trials is random. Those are just shifts of each other. So same idea. I think we all know what distribution experimenter 2 believes this is distributed as. Does anybody know the name of the distribution that experimenter 2 is presupposing with this assumption? I'm going to talk like that from now on. So we're allowed to use our outside voices. So what's the distribution? It's negative binomial. So does anybody know what a negative binomial with just, we're just generating data until the first head occurs? That's a geometric distribution. Sums of geometrics. So if sums of 5 geometrics is going to be a negative binomial with 5 successes being fixed. So just things that you can put into your quiver. Next week in chapter 7, we'll be touching the negative binomial distribution a bit, so you probably want to look over that over the weekend and study the 2 different parameterizations that the book seamlessly goes back and forth between. So I've noticed that confuses people. The 2 different parameterizations has to do with whether or not you said the number of failures is fixed, or the number of failures is random, or the number of trials is random. So one is just adding in the number of successes, shifting over that distribution. So fifth head, so I'll just say coin flipped until the fifth head occurs. So this is experimenter 2's belief. I think both beliefs are reasonable because we just have no idea. So I will point out, doing analysis on DNA sequences is just like this, that they'll make assumptions about why there's a certain number of base pairs in your sample. They do all kinds of assumptions like that. And the question is does it change your inferences? I'll just point out, if you do a likelihood-based inference, it doesn't matter. And if you do something other than that, it could matter. So we'll see that in this example. Okay, so experimenter 1 is basically saying that the data is distributed in a binomial fashion. So binomial distribution models the number of successes with a fixed number of trials. So, and it's fixed right here. And so what experimenter 1 is saying is that the number of successes is random. So experimenter 2 is saying that the number of failures is random. And that the length of the data set itself is random. So slightly different. So I'll just write down, this is fixed. The 5, and they're saying that it's negative binomial. I.e. the failures is random. I'll parameterize it that way. And this is saying that the number of successes is random. Successes are random. So slightly different take on this data set, but both experimenters think that the data generating mechanism is exactly the same, i.e. it's an IID coin flip. So let me just write this down. 5 successes are fixed in advance. The only reason experimenter 2 says this is they just spot there's an H in the last thing. So I'll just make an arbitrary rule about what I think the stopping rule on collecting this data is. And so the question is should that matter that experimenter 1 and experimenter 2 agree on the model, almost, except for the stopping rule? And should that make a difference in your inference? So if you subscribe to the conditionality principle, then probably not. It probably shouldn't matter to you. So let's just write down likelihood functions for both experimenters. So let me just write down X is the number of successes and Y is the number of failures. So this is random. Successes are fixed. And the number in this right here for experimenter 1, I'll just remind us, this is experimenter 2's belief. And experimenter 1 thinks this is random. And N is fixed. So the X and the Y here are just the two different thought processes for experimenter 1 and experimenter 2. The actual data set is exactly the same. What they think is random is different. So this is, even though it's exactly the same data set, the thought processes are different. So this will help you to match the notation on what we wrote down before, that you have two likelihoods that are proportional and they're conditioned on different beliefs. Okay, so experiment 1. Experiment 1's distribution looks like this. N choose x, p to the x, 1 minus p to the n minus x. So that's the binomial distribution. And probably somebody could wake you up at 3 o'clock in the morning and say, please explain to me the binomial distribution and where this binomial coefficient comes from, and you can probably do it real quickly for somebody. So this is the different number of ways that I can rearrange this data set. They're all IID, so I'm just producting together the probabilities. Okay. So experiment 2's distribution looks a little bit different. Now, I don't ever memorize what the negative binomial distribution looks like, so I re-derive it every single time. So let me show you how I re-derive the distribution and make sure that I get the normalizing constant correct. So I'll draw you a picture. It's a negative binomial list. So there's 10 dashes there denoting my 10 data points. What experimenter 2 is saying, the only pre-assumption that they're saying is that this last trial right here was ahead. So if it's negative binomially distributed, it has to end on a success. So, and it doesn't matter which order the heads and tails are in here. Now, of course, if I saw all the tails up front and all the heads second, I'd probably start thinking this wasn't IID. So, but that is possible if things were IID, but if I saw it that way, I probably wouldn't believe that it was IID. And if I saw that in practice, I'd probably say, go get me another data set. I want to see if that last trial is actually in H. So, and if it's not, then I might believe experimenter 1's assumptions about the data. Saying that we can't do any of that. So all we're saying is that this last trial is ahead, and that there's 9 trials here. With 4 successes. So this was the 5th success. In these 4 successes and 9 trials can happen in any order. It doesn't matter, because everything's IID. And so this stuff right here has a binomial distribution. So 4 successes, 9 fixed trials in there. So the distribution for this stuff right here looks like this. 9, choose 4. P to the 4, 1 minus P to the 9 minus 4. So it's binomial distribution. And I know what the probability of this thing is, right here. It has probability P of occurring. So what do? I multiply them together. So if I understand what the binomial formula is, I can always derive this. So and it looks like this. So this is going to be 9, choose 4, P to the 5, 1 minus P to the 5. So this is also 5, right here. So the correct normalizing constant here is 9, choose 4. And I'll point out for our fixed data over here, experimenter 1's thought process, this right here is going to be 10, choose 5, P to the 5, 1 minus p to the 10 minus 5, which is 5. So experimenter 1 and experimenter 2 are going to write down two different distributions, and they look almost the same. This part looks the same. This part looks different. So effectively, experimenter 1 and experimenter 2 are arguing about the normalizing constant. And they're different from each other. But what I want to point out is that this likelihood function is that likelihood function. They're exactly the same. So let me write that down real quick. So note, likelihood of p given x, this is experimenter 1, is going to be equal to, I'm writing down equal, but what I always mean is proportional. So this is 10, choose 5, p to the 5, 1 minus p to the 5, which is proportional to p to the 5, 1 minus p to the 5. So this is really the likelihood right here. So experimenter 2, I'll say given y is proportional to, or it's, I'll just write down equal, but what I really mean is proportional. P to the 5, 1 minus p to the 5, which is proportional to p to the 5, 1 minus p to the 5. So same likelihood function. Experimenter 1 and experimenter 2, if they adhere to the likelihood principle, should have identical inferences. I think that makes sense. So presupposing that they agree on how to use the likelihood. So that's the part that's missing from the likelihood principle, what to do next. So presupposing they're going to follow the same inferential procedures from here on out, and they're going to do a likelihood-based analysis, maybe a Bayesian analysis with Jeffreys prior or something like that. So maybe they're going to use a beta prior with parameters half and half. So I mentioned during review there's good reasons for that prior. So we're not going to cover all those reasons in this class. But in Bayes class, this would be like week 1 or 2, and we go into depth about that. So if you want to know more, take that class. So experimenter 1 and experimenter 2 should agree. I want to be a little bit more clear about this formula right here, just what is random in everything. So let me just write this out a little bit more. So this is going to be y, the number of failures. Let me give myself a little bit more room. Let me put it there. So we wrote down 9, choose 4, p to the 5, 1 minus p to the 5. There. So I want to be more clear about this and write it out in terms of y, what's actually random. So this is going to be y plus 5 minus 1. That's my number of successes minus 1. And this is my number of failures. This is my number of successes right here. And I have the minus 1 in there. So if I just added this whole thing up right here, this would be a 5. The number of failures that I observe plus 5 minus 1, which is the 9. So I'm just parameterizing it in terms of the number of failures. And this right here is going to be 5 minus 1. Number of successes minus 1. So that's where those numbers actually come from. And that 5 is fixed in there. This is going to be p to the 5. So this 5 right here, that 5, and that 5 were all fixed in advance. So that's my fixed number of successes that I'm looking for in advance. So times 1 minus p to the y, the number of failures. So I'm just parameterizing it in terms of the number of failures. Sometimes people parameterize it in terms of this number and call that n and let that be random. So that's the difference in the two notations or the two parameterizations. You could also shove the y down here instead of the fixed thing. So you can have the same exact binomial coefficient. So there's lots of different ways to write this thing down. Okay, so that's the negative binomial distribution. Experimenter 1 and experimenter 2 should agree. Let's imagine they're not likelihoods, and they're about to violate the likelihood principle by computing a p-value. Okay, so I'm going to switch gears a little bit and do something that is meant to be contentious. So it's designed to make sure that these two experimenters' conclusions do not match each other. So if they do a p-value based analysis based off of these two distributions, that is going to happen. So let me just ask you guys, what is a p-value? Let's write down the definition. This doesn't come up until chapter 8 in the book, but we've all had a prerequisite that touched a p-value once upon a time, right? Somebody raise their hand if you've never seen or heard of a p-value before. Dan? So, not yet. So let's just review real quickly. So this is Stat 101 stuff. So if you took a first ever stat class, you probably were exposed to a p-value. So they probably gave you some definition of it. This will make a little bit more sense in chapter 8. But I'd say any elementary text on statistics probably teaches you all about p-values. I know I took a Stat 101 class once upon a time, and that's kind of all we did. State the null hypothesis, compute the p-value, conclude something. So over and over and over again. So they're turning me into an algorithm. So turning me into a robot and computing these things. Let's see if we understand what they are. So let's just write down a definition. P-values. So what is a good definition? This should also be something that most of you should be able to get woken up at 3:30 in the morning right after you've explained what the binomial distribution is to somebody. And they wake you up and they say, hey, what's a p-value? What would you tell them?
Probability of observing a result that's at least as extreme as what you've observed in your data based on some distributional assumptions.
Okay, so it's the probability. Let's at least write down this part. The probability of observing your data or more extreme data based on some assumptions. This is the part that I usually hear people say slightly off or they omit. So what is the assumption?
That your null hypothesis is true.
That's it. So conditioned on your null hypothesis. So let me just draw a quick picture. This might refresh some memories. So just a quick example. This is the most contentious p-value that I'm about to draw a picture for. We'll come back around to this in chapter 8, and I'll tell you why it's so contentious. You can get no agreements out of anybody if you do these sort of analyses. I'll also point out this is the most common analysis I ever seen done. So just a quick example. say I've got xi's coming from a normal distribution with mean mu and variance sigma squared. Everything's IID, I get to see n data points. I am going to presuppose that I know this, so the analysis is really easy to do. And I want to say something about mu. I'm going to say this right now. I do not think we should be teaching this example to Stat 1-1 students. They don't know what they're doing with it. And also the question really should be just estimate mu. So don't do this thing, train people to, let me presuppose what I think mu is and then use a p-value to potentially test against it. So estimate mu. Just tell me what you think mu is and give me your uncertainty on that estimator. So x bar would probably be the estimator. If you give somebody, you probably want to quantify your uncertainty about that. So it probably has something to do with sigma squared over n, i.e. that evidence function. So this is what is the notation for a null hypothesis. So this is just your hypothesis. So the whole terminology, null hypothesis, it's just your hypothesis, what you're hypothesizing about. So we might do something like this, mu is equal to mu naught. So the question mark is mu naught. So I'm going to test this thing at a point right here. So that's the question. I will answer this question right now for any real problem. No, you did not pick the right mu. I already know that. So the question really isn't this. When we jump into chapter 8, I'm going to argue about even asking this question. That it's not. The real question is, are you close to mu naught? And what you need to define is what's close to you. That's what Bayesians and non-Bayesians are arguing about, is their definition of closeness. So one is absolute in terms of their distance function, and one is relative. So that's what they're debating about. So in very simple terms. We'll come back around to that. But I can already tell you, no, mu is not mu naught, unless you've cheated. So, because there's an infinite number of values out there, and that's just one value. So if I compare that one value to an uncountably infinite collection, that has zero weight. So that's what I think. So I think that the p-value is trying to ask this question of, do I think you're close to mu naught? And then they'll quibble about whether or not it's statistically significant and practically significant. And they'll go, oh, well, just because I said it's statistically significant doesn't mean I think it's practical. We've all heard that before, right? Statistically significant, but it's not practically significant. Let me give you an example. If I were flipping a coin, and I asked this question, is p 0.5? And I flip the coin a bazillion times, and I find out that the probability for that coin, the relative frequency, is 0.5000001. And I can measure that with certainty, that it's not 0.5. So I would maybe, if n was very high and I were doing a p-value based analysis, I would reject that p is equal to 0.5. But then I might say, but it's really close. So I'm just able to distinguish the difference between those two things. So being able to distinguish the difference in some probability sense is what statistical significance is. So, but then you might say, but nobody really cares, because it's not practically significant. So that's a more qualitative concept. So my usual response to all of that is then, why are we doing it? So if it's not practical. I'll say more about that in chapter 8. So the alternative hypothesis, this is really contentious, is mu is not equal to mu naught. These p-values that people compute and posterior probabilities on this null that maybe Bayesians would compute have nothing to do with each other. They are totally unrelated to each other, the calculations and the meaning. So I will also say the one-sided p-value, so if that's an inequality right there, the correspondence between the Bayesian and the non-Bayesian, there is a correspondence between them. They kind of agree with each other. Again, I'll say more about that in chapter 8. So the p-value that you would end up computing for this would be based off of your null distribution. So your null distribution is centered at mu naught. We have n data points, so variability that we're going to plug into this is sigma squared over n. Then we're going to look at where x bar is. So let's say my actual x bar, which is just the sum of the xi's, divided by n, I'll point out that is the sufficient statistic. It's minimally sufficient. And so doing inferences with a whole collection of xi's and doing inferences with just x bar are exactly the same, because that is the min sufficient statistic. So we're going to look at x bar over here, and we're going to compute this tail probability. But because we could err on either side of all of this, this is the two-sided test, and we end up computing over here, this is also more extreme stuff. So this is the more extremity. This is where your actual data lives. This right here, this reflected point on this other side, just the same distance away from mu naught, is also just as extreme in direction. And these are more extreme values. This is more extreme. This is more extreme. So if we were just doing a one-sided case, mu is greater than mu naught, then we would only use that as the p-value. The p-value R is the shaded area, right here. So that's a p-value based analysis. So this is the p-value, right here. So hopefully that jogs your Stat 101 memory of what they tried to indoctrinate you with. Has everybody seen this before? We'll go through a little bit more detail when we get to chapter 8, but I kind of assume that you've seen this before. Okay, let's go back to our actual example. So the more extreme stuff is kind of weird. And if you feel like that's all kind of weird, why is that actually a paradigm? What is it doing? Does it make sense? Here's what your Stat 101 teacher will usually tell you. That if the probability of what you've observed and more extreme stuff is incredibly low, then probably what you've assumed in the first place is not true. So the hypothesized value, the null hypothesis, is not true. It could be other things. It could be that your whole model is wrong. So what you're really rejecting is just your whole model. So it might not be your null hypothesis that's wrong, but all your modeling assumptions might be wrong. So that's troubling. So what you're really doing is rejecting the entire model, or at least this is some proxy for evidence for it. So that's the idea that people say, oh, that makes sense. I get it now. Let me tell you what Jeffrey said about this. I pulled up this quote this morning. It's one of my favorite quotes. Jeffrey said, is famously stated by Jeffrey's 1961 in some book on page 385. What the use of P implies, so P is the p-value, so what the use of P implies, therefore, is that a hypothesis that may be true may be rejected because it has not predicted observable results that have not occurred. Can I read it again? What the use of P implies, therefore, is that a hypothesis that may be true may be rejected because it has not predicted observable results that have not occurred. That's also the same logic as this Stat 101 thing that everybody's talking about. What they're saying is the things that haven't observed are the more extreme values. So I'm going to reject something that may be true based off of values that I never saw because they didn't happen. Why are you averaging over this stuff that's more extreme that you never saw in the first place? And so that's the problem Jeffries has. He says it makes no sense whatsoever. It makes a little bit of sense. So, but I would say it has some semblance of being logical, but it's not entirely logical. So we'll confront all this pathology in chapter 8. That's what chapter 8 is today. Okay, so here are the p-values. So experiment 1. Oh, let me give you some hypotheses. So let's say experimenter 1 and experimenter 2 are interested in testing this hypothesis, P is equal to P naught. And they're going to look at a particular tail direction. And they're going to compare this to P is greater or equal to P naught. I want to make a note about this. This is the standard notation that you would see in your Stat 101 class. It'd say the hypothesis is P is equal to P naught. And the alternative hypothesis is P is greater than P naught. What they really mean when they write this down, let me get rid of that equal sign right here. What they're really testing is P less than or equal to P naught versus this. So the person that's going to compute the p-value, so I'll say the Neyman Pearsonian. So Neyman Pearson is all about p-value calculation. So the p-value is the Neyman Pearsonian wants to test this against that. It turns out the most evidential point in the set is when p is equal to p naught. So that one has the most power to detect and weigh the evidence of the null against the alternative. So that's the most powerful point in there. So that's why you always see in Stat 101 that they condition on this thing. Also keep in mind, you're going to condition on your null hypothesis. You can't condition on a set, but you can condition on a value. So if I have a normal distribution, I can plug in mu naught, but I can't plug in a set of mu's. There's no way to do that. So you're going to pick the most promising point in the set to test against this. So the correct terminology, they say, is you can reject the null in favor of this, but you can never accept the null. So instead they say you fail to reject the null. So you can never know anything with certainty. So I don't care about any of that. If you say accept or reject, I'm okay with that. At the end of the day, you're going to make a decision. So I don't care how you phrase it. So it doesn't matter to me. I do get the Popperian thing that you can never know anything for sure. So you can't accept anything. All you can do is falsify things. So that's science. Set up a conjecture, try to falsify it. If you can't falsify it, it becomes a theory. So if you just admit, we've tried to test against it over and over again, but that's what makes something theory. Okay, cool. We all know that. So here's experimental one's p-value. I also want to point out p greater than p naught in this set right here. This would imply more successes. This would imply also less failures. So as p gets bigger, you can see more successes in your data set and less failures. So the more extremity is over more successes or less failures. So that's the tail direction we would compute for everything. So experimental one is going to compute this p-value. It's going to be sum. X is going to go from 5. That's what you've observed, the number of successes. So that's observed. And it's going to compute all the way up to n, which is equal to 10, and that was fixed in advance. So that's the most extreme value. So, and then they're going to plug in this binomial distribution and choose x, p to the x, p naught to the x, 1 minus p naught to the n minus x. So this is experimental one's p-value for testing this hypothesis. And if you've taken Stat 101 recently, they probably had you do this sort of thing over and over and over again until you stop complaining that you didn't understand it. So, experimenter 2 computes. Let me write it over here. Experimenter 2 is thinking the random variable is failures. So the more extremity is less failures, not more failures. And we know that by looking at the alternative hypothesis. So when you compute a p-value, you're chasing the alternative tail direction. So that's the way I always think about it. If you want to think about this a little bit differently, if you're not sure if you summed over the right side, take p's bigger than p naught and start plugging them into this equation. And if the probability starts going down and down and down, for that, you've computed the right thing. Because that's the thing that's testing against the null hypothesis. So that's when you would reject it. So this is the correct tail direction. So the negative binomial tail direction is this. So the p-value for experimenter 2 is going to be sum, and this will go, I'll just plug in this thing right here. This will be y plus 4, choose 4, p to the 5, that was fixed. This is p naught, 1 minus p naught to the y. And the question is where do I sum from? Y goes from what to what? This usually gets people at 9 o'clock in the morning. So, and it's because of what Jeffrey said. None of this stuff really makes sense anyway. It's confusing. So, but the more extreme direction is less tails. So this would be y goes from 0 to 5. That's what you observed. And this is the more extreme stuff. Y is equal to 0, y is equal to 1, y is equal to 2, or y is equal to 3 or 4. Those are the more extreme values. So what I want to just point out is this and this are different. They're different numbers. I'm sure for some p naught you could make them the same, but across different p naughts, it's a different function. So they sum up differently, they're not the same thing. So here's the point. So key point is star is not equal to star star. So experimenter 1 and experimenter 2 would compute two different p-values. So because of the way that they're thinking about what the stopping rule is, and that's it. So let me just say this. If you're a likelihoodist and you're doing a likelihood-based analysis and you weren't violating the likelihood principle, experimenter 1 and experimenter 2 would agree. And if you ended up doing this more extreme stuff and you're summing over more extremity, which is a violation of the sufficiency principle. So, sorry, let me say again. It's a violation of the conditionality principle. You haven't conditioned on that. You're averaging over stuff that you didn't observe. So that's what this is all about. So violation of the likelihood principle, the p-values don't agree. I will say this. If you do walk up to people's analyses and go, violation of the likelihood principle, you walk away from them, you'll piss them off. So let's come back, say a few more things about this, answer some questions about it, and then we'll be turning the gears and moving into chapter 7. Chapter 7 is probably the easiest chapter that we have because it's all just calculations instead of principles. Okay. Have a great weekend, you guys. Enjoy basketball season.